Okay, so in chapter 6, our main goal that we're going to be studying, like pretty much through the end of the year now, is looking at normal distributions. And we've already looked at normal distributions, like you should be thinking about the empirical rule. And I know we talked about this slightly in chapter 5 too, how we were looking at within a certain number of standard deviations, we had a specific probability that would lie between that. And so you should be thinking like that whole rule that we had of like 65, 95%, and 99.7. So we know that within like one standard deviation and two standard deviations, but we also know that you can be like 1.2 standard deviations away from the mean. So today's lesson is just kind of looking at the probability within a certain number of standard deviations, and especially when you don't have like a really nice whole number like 1, 2, or 3, or negative 1, 2, or 3. The reason why normal distributions are so important is that so many things in nature actually follow a normal distribution. So it's probably one of the most important distributions in all of statistics because so many things actually do behave normally. And then that means that we can make some assumptions about like how far people are away from the mean and like what that means as far as if something is statistically significant or not. If you know how something behaves, then you can see some sort of outlier. You can see an abnormality on the graph. And that's what statisticians do is they conduct an experiment, they have some sort of control, and they conduct a different experiment where they change something and they see if their results are statistically significant from the first results. So anyway, background information is basically just saying like, so many things behave normally, so we have to understand how normal distribution works. So we know kind of what normal distributions look like. They're mounded in the center. They look like a bell curve. The actual function for a normal distribution is a little bit complicated. It looks like, this 1 over sigma root square root of 2 pi, blah, blah, blah. But we're actually not going to use that function. Instead, like, that's actually modeling what that stuff is. But instead, we just have to know that it kind of exists, because if we have a function that we can model, then we can do some things to that function. And so that's what today's lesson kind of comes in. There's some important characteristics about this normal distribution that we should be aware of. One is that the total area under a normal curve is equal to 1. And the reason for this is since we're looking at a probability distribution, and we're going to say that this probability distribution behaves normally, we know from our rules of probability that all probabilities add up to 1. So what we're going to do today is talk about the area underneath a curve, or the area within this normal distribution, and say that it equates to some sort of probability. So that means that the total area that we have under the curve should be equal to 1, because all probabilities should be equal to 1 too. And then we also know that this distribution is symmetric. That's pretty standard. We talked about that when we talked about normal distributions before. And then we also know that I lost one. Well, sorry, I think you have that on your sheet. I don't know why that's not showing up. But the distribution's mean is at the center of your distribution. It has a z-score of 0. And that's because, and we've refreshed z-score recently, that the z-score is the value minus the mean over the standard deviation. And if you do mean minus mean over standard deviation, you should get 0. So right in the center, we have a z-score of 0, but anything to the right of that, anything in the positive direction, we have positive z-scores. Anything to the left of that, we have negative z-scores. So we can kind of see that on our graph. And we already know what standard deviation is. We've been talking about that all year long. It's the average distance away from the mean, or the typical distance away from the mean. And then we also know that most of our probability that we have, most of our data, if we conduct some sort of experiment, most of it does fall within 3 standard deviations. We usually don't have like a 4 standard deviation or a 5 standard deviation. Those are usually classified as outliers. And we already know this because we've talked about before, the empirical rule tells us that 99.7% of our data falls within that range. So usually when we conduct find our z-scores, we're between negative 3.00 and positive 3.00. And again, a couple key characteristics about z-scores that we have to refamiliarize ourselves with. One is we always round them to 2 decimals. So we always round it to the nearest hundredth. And then also that like negative and that positive means something. It tells you if we're below the mean or above the mean. And we've already like put this on a graph. That mean would be, significant to some sort of number. Like, last chapter, the mean is 2, our standard deviation is 1.4. So we can find like these, corresponding x values on our graph that would be one standard deviation below and one standard deviation above by adding and subtracting that standard deviation to the mean. So what we're going to do today is talk about the probability that lies within a range. So the probability within a certain two x values, so we're going to say it's like a and b, would be equal to the area underneath the curve. And so that's a pretty important distinction for today, that this, this area that we're looking at, this range of values that we have, really actually corresponds, since we're kind of relating this to a probability function. This would actually correspond to the probability of, something happening between those two values. So sometimes that's symmetric because we're looking at like, values between -1 and 1, or values between 2 and 4 or something, and we have something that is symmetric about the mean, but it doesn't have to be. An example of that would be like, given a test and you have 20 students in your class, find the probability that 18 or more will pass the test. And we did that with like a binomial function, but we could also like come up with a linear or a normal distribution that would look like that, and then we could actually calculate the probability of 18 or more on our graph. So we could display it graphically, but also we could look at it with a function and calculate it numerically as well. So notationally, what that looks like, and not that you need to know this, but notationally what that looks like is that we are looking for the probability from A to B on an X range, and that in calculus is actually represented by an integral. Again, not that you super need to know that, but that's actually where it's coming from. That's why when we talk about like the area underneath a curve, we'd have to end up doing some, integral of this crazy function, and these values that we had of something like 1.45, which we couldn't actually calculate until now, is something that someone did calculate with calculus, and that's how they got all these, corresponding probabilities. So for our first example, let's say that we're finding the area, which again is really looking at the probability between 0 and 1.45. Before, when we did this, we did 0 and 1 and 0 and 2 and 0 and 3, and then we found, like, if you remember, we like shaded in that region, and we found that like our first one was 68% between one standard deviation, and so half of that was 34% on one side, and the other half was 34% on the other side, and so that worked with like one standard deviation, but we didn't do like 1.45. We didn't do 1.6 standard deviations away, but we know that those things actually exist. So instead of doing calculus and statistics, which we're not going to do, someone did calculus out there and created a nice little handy dandy note sheet for you. So if you pull out that like areas of the standard normal distribution, you can see like that picture on the top that says that we're looking for the probability from 0 to z. And you can see that like all these probabilities on this sheet, the highest that we end up going up to is 0.4999. And that's because we're always looking at from 0 to, some positive z-score. And so that means that like, half of our probability lies on one side and half of our probability lies on the other, meaning it is symmetric. So all these z-scores that we have are all something that's positive. But we know that like the z-score of negative 1.45 to 0 would also be the same area. It'd be the same probability going in that direction as well. So the way we read this chart, if we're looking for the z-score of 1.45, we use our like first, tenths place, and then the hundredths place is located on the top. So we are looking for 1.4, and then we'll go over to the 0.05, and we'll see where that lines up, and we get a probability of 0.4265, or an area of 0.4265, which again corresponds to 42.65% of your data would fall within 0 or 1.4 or 5 standard deviations above your mean only. Okay, notationally, how we would write that is that the probability between 0 and 1.45 inclusive would be 0.4265. So today, mainly, if you understand that idea, that's great. Most of what we're doing today is going to just be like calculating and manipulating this table a little and looking at the area between a couple other z-scores. So let's do another one. Well, first off, while you're doing these, sometimes it's really helpful to like create some sort of sketch, because if you are finding your z-score of this one to this one, or 1.2 to 3.0 or something, it's helpful to see what that looks like, so that way you can actually get a plan of attack and calculate these a little bit easier. And then also, we already talked about this actually, the symmetry of the normal distribution is really helpful. So if you know that the probability from 0 to 1 standard deviation above it is the same as 0 to 1 standard deviation below it, then that means that you can kind of just like draw your picture on the left, but know that you're still matching it up with the positive values of your z-scores on your chart. Okay, so let's do another one. We're finding the area under the normal curve to the right of z equals 1.45. So we already looked at like 0 to 1.45. Another way to represent that would be the probability of z is greater than 1.45. So you probably see both of those. So if I draw a sketch of what that looks like, if I have my normal distribution, I'm going to find 0, which is my mean, and then I'm going to look at 1.45, which is located to the right of 0. So higher standard deviation, higher z-score, so something that's positive to the right. We're looking for something that's above that, so we're shading in like the tail end of that. Knowing that we have symmetry means that from 0 to all the way to any positive z-score is going to be 50% of our data, 50% of our area. So that means that the area is going to be 0.5, but we're looking at that tail end of it. So if that whole thing's 0.5, and we already know, because we already calculated this on the previous problem, that from 0 to 1.45 is 0.4265, to find the area, we'd have to subtract it from 0.5. So again, notice on your chart that the tail end of this probability is not calculated for you. And that helps you like match up your picture with your picture. And it helps you decide if you have to subtract or add or whatever you have to do to actually get that corresponding probability. That picture on the top of your chart will help you because it tells you what that area is actually representing. So from 0 to z, 0 to 1.45 is the 0.4265. So that means that we're looking at the stuff that's greater than that. It's not corresponding to the 0.4265. Okay, let's do another one. So this one, we're kind of doing a combination. We're finding the area to the left of 1.45. So again, if I draw my picture, I'm going to have that important value of a z-score of 1.45 to the right of my mean of 0. So label your important pieces, 0 and 1.45. This time, instead of going to the right, which is that little tail end, we're going to go to the left. So we're looking at all the values underneath that. So again, using your symmetry can be helpful. This time, again, we've already calculated from 0 to 1.45, but this time we're including past that and all the stuff to the left, which we know the stuff to the left is 0.5, and we know from 0 to 1.45 is 0.265. So this time, if we're looking at our z-score being less than 1.45, we would add our probabilities together, and so that would account for 0.9265% of our data. We also could, if we wanted to, since we've already found the tail end of the z-score being above 1.45, is we could subtract the 0.0735 that we saw, for example, 2 from 1, and that should give us the same answer, because that value, again, everything under our curve is equal to 1, and we've already found like the complement of that event happening. Couple more. So this one says that we're looking at the area between the mean and negative 1.26. So again, if we were drawing what this looked like, we would be putting our important value, our z-score, at negative 1.26. But again, we know that our z-score, positive 1.26, is also the same area. So we can use our symmetry and our table in that way to calculate this area from our table. And again, like make sure that you can read your table. So take a second right now and look through your table and find 1.26 and make sure that that actually matches up, or you can read that to get the right answer of 0.3962. So the probability between negative 1.26 and 0 would also be the same as from negative 1.26 or 0 to positive 1.26, which is the 0.3962. So all of that we did was 6.1. So we're also going to, because it's a really, really similar idea, we're going to look at 6.2 as well. The difference here is that we're like doing still some sort of combination of events, but instead of we just kind of use our table, the combination that we have is just like a little bit more challenging. Now this one again is like pretty similar to the one we just did. We're looking at the area to the left of negative 0.98. So again, like on our table, if we were to draw a picture for that, we put negative 0.98 as a z-score to the left of our mean. So like mark that now. And I always draw like a vertical line going up so I can see, since I'm marking off these areas. And I'm looking to the left. So if I were to shade this, I'd be looking for that blue region there. However, I know if I can find the region from 0 to negative 0.98, and then I can subtract that from 0.5, then I can come up with that tail end. But I can't look up negative 0.98 in our table, but I can look up positive 0.98 in our table. And that value would be 0.3365. So the probability between, or less than negative 0.98 should be 0.5 minus that 0.3365, which is 0.1635. Same kind of idea for number 6. Again, it's not too complicated. It's not something that we hadn't done. We did something really similar to it, like it in example 3. But this time we're looking at it between two different z-scores. So for this one, when I draw my table or draw my graph, put 0 again in the middle. I should have 1.8 above my mean of 0, and then negative 2.3 below my mean or below my mean, which is my standard deviation of 0. And so it looks something like this. And so I want to find that whole area, which means I'm looking at a combination of two different areas. One is from 0 to 1.8, and one is from 0 to negative 2.3. So I can add those two areas together, which means that I can look up both these values in my chart. And again, negative 2.30 is the same as the positive 2.30. So I'm looking at that value. The 1.8 should be 0.46 or 0.4641. So the probability between those two should be, then adding those two would be 0.9534. So tons and tons of our data actually lies between the negative 2.3 and 1.8. And that actually should sound kind of familiar because we know that 95 approximately % of our data lies within 2 standard deviations. So this is basically close to 2 standard deviations. We're a little bit under on the positive side, but a little bit over on the negative side. And so that's roughly approximately the 95% of our data within 2. Okay. Seems again like a little bit more challenging yet. So drawing a picture of this, both these values are negative. So I draw my mean. I draw negative 1.4 further to the left, negative 0.5. That's in between negative 1.4 and 0. And I'm looking for that area that resides between them. So this is the area that I'm asked to find. So in order to find that, what I should do probably, since I can only look up 1.4 and negative 0.5 on my table, the kind of process for this would be if I found all of negative 1.4 and then subtracted off the area from negative of 0 to negative 0.5, that should give me that area that's in between. So that 0.4192 should be the area of negative 1.4 to 0, and then the 0.1915 is the area from 0 to negative 0.5. I think there's 2 more examples, And this one is a teeny bit different, and it's kind of similar to, like, it's a combination of like working with percentiles and the values that we did before when we talked about standard deviation. So in this case, though, we're not actually given the z-score. This is what we're actually trying to find, is we're looking for the z-score that would be associated with a certain percentile. So the 85th percentile, remember, means that 85% of our data lies below that value. So if you're in the 85th percentile, that means you're on the upper end. You're above the mean. The mean is 50th percentile, like smack dab in the middle. So we're above that. So if we're going to draw a picture of what this looks like, 85% of our data would be under it, which means that I'm somewhere to the right. Okay, so if I want to look up a corresponding z-score, I can't look up 0.85 or 85%, and I can't have a z-score that I'll look up. So I have to work backwards and use my chart, which is my percentage, to find the z-score that would closely relate to that. But again, like, my chart only goes up to 50%. It only goes up to 0.499. So in our case, if we were trying to figure out like what we need, I know that this includes 50% of our data from, the left-hand side to that point. So what my chart was going to tell me is, or what I really need to look up, is 0 to whatever that z-score would be. So that piece that I have, since I know that the tail is 0.15, that piece that I need is 35%, 0.35. So I'm looking in my table, I'm looking for that percent because that'll allow me to find my z-score that's associated that would give that percent and have all my data that's less than that be 85%. So in my table, I'm looking for the value that's closest to it. So my data that's closest to that would be 0.3508. That's the closest value that I have, which means that the z-score that closely responds to this, or the closest one, would be 1.04. So again, I'm working backwards in that case. So if I asked you now to say what percent of the area, or what percent of our data, what's the area below a z-score of 1.04, you would do 0.5 plus the 0.3508, and that would be 0.8508, which is about the 85th percentile. Last one, looking at the z-score that is bounding in the middle of a 90% of a normal distribution. So that problem is a little different because instead of looking at a value that's totally less than that, we're bounding our data by two z-scores, a negative z-score and a positive z-score. And since we're symmetrically bounding that, our z-score should be the same as a negative and a positive. So if I was going to graph this, I'd be looking at my mean of 0 and a positive z-score and a negative z-score, and that splits my 90% right in half. So I should be dealing with 0.45 and 0.45 on either side. Again, working backwards means that I'm looking at my chart and I'm looking for 0.45. So pulling that out, I am finding the closest resemblance to 0.45. And this time, last time, like, we just found the closest one, but this time 0.45 is halfway between these two values. So if that's the case, if it ends up being exactly in the middle between two values, we always round up to the higher one. So in this case, our z-score that would be bounding the top and bounding the bottom would be negative 1.65. And again, this is kind of a big day because if you understand this lesson, then you have a better understanding of all the applications that we'll do later. So always draw your graphs because it's super, super helpful to see, like, if you're adding or subtracting, and it's super helpful to see if you're having a positive z-score or a negative z-score or where you are on your graph. It's really, really, I promise it will be helpful in the long run. Even if you can do it without it right now, keep drawing your graphs because it's going to be more beneficial to you later. And then also, you need to have this chart when you do your homework because otherwise you won't be able to actually do any of it. So make sure that you have that handy. For homework over the weekend, you have stuff on page 284. The answers are on the next slide. I know it says quiz, but we're going to do a combination quiz on Tuesday rather than a quiz on Monday. So just complete your homework and then make sure you come in with any questions that you have on Monday.